Alrighty, hello and welcome back to a whole new chapter of our lives here together, our online lives. So we are done with chapter 1, our first order differential equations. In chapter 2, we are going to focus on higher order linear ODEs, right? Okay, so higher order, what do we mean? Well, chapter 1 was first order, so what's higher order? Second order, third order, fourth order, nth order. Okay, so that might get you excited, scared, who knows, we'll see. The word linear ought to make you a little bit happier because, you know, we saw when nonlinear got involved, things got a little crazy. And we're still in ODEs, right? So we're going to focus first on second order. We'll start there, then we'll generalize the ideas to higher order, okay? So section 2.1 is second order. Well, it's beginning to talk about second order linear ODEs. We're not going to really, we're going to leave 2.1 in various places. So we're picking out little bits and pieces of 2.1, but we're really moving to 2.2 right now, and you'll see why in just a sec. Second order linear ODEs. Okay, so second order. So what does a general second order ODE look like? The most general one would be having some generic function that depends on an independent variable. We'll just go with x because it's easy to write. We'll call x our independent variable, y our dependent variable. We're used to that, but again, it doesn't matter what the letters are. They can be any other letters, so we're still good. And then if it's a differential equation and it's second order, then we could have derivatives of y, first derivatives of y, and also now second derivatives of y, okay? So we can just have some big messy combination of x, y, y prime, and y double prime, and, you know, move it all over to one side of the equation. Z equals 0, good luck solving, okay? And literally good luck solving. So in general, right, if things are nice, we could solve and get y prime, solve this equation for y prime, and get y double prime, that's where we are now, second order, right? Second order. Y double prime is some other function that just depends on x, y, and y prime. Okay, so you basically isolate y double prime. Well, notice here, right, this isn't going to be as nice as what we did visually and geometrically when we first introduced first order equations, because, you know, y double prime is talking about the concavity of the solutions, and then you're going to have slopes and everything all mixed in, right? And so in first order, when we solved this, you know, and that wasn't there and this was a y prime, we were able to visualize the slope fields, what was happening with solutions that would satisfy that differential equation, and that's not as easy with second order. Does that make sense? Okay, so it's doable, but nowhere near as easy. Anyway, let's come back then to what we are going to do. So what are we going to do? We're going to talk about linear guys, right? This would in general be nonlinear, okay? So we're thinking of this, these guys are nonlinear, okay? Because any type of combination of function involving y or y prime could happen, and, you know, that's not linear, right? So if we're linear, okay, so now we want to go linear second order, then we're going to be able to write this type of a thing in such a way that we can write it as some function of x times y double prime plus some function of x times y prime plus some function of x times y is equal to some function of x, right? And you probably could have written that down before I did, because we're so good at this now with understanding what we mean by linear differential equations. Linear in the dependent variable, right, and all of its derivatives, right? Okay, linear in y, y prime, and y double prime. Okay, so, well, what? Well, one big difference with first order, right? If this was first order, we just divide by b of x and then call that p of x and that g of x, and we have a solution formula for all possible equations, right? That's crazy. That ain't happening with second order. As soon as we go to second order, you're not going to get a general solution formula for equations that look like this, even in linear, okay? And in particular, it can be, we are going to get existence and uniqueness theorems for initial value problems for second order initial value problems. So that's going to be nice for linear, guys, okay? Non-linear, big wild world out there. But even for an equation that looks like this, it's extremely difficult for particular functions a, b, and c of x to actually find solutions of the differential equation, okay? Particularly difficult. In fact, unless these functions of x that are multiplying the coefficient functions, right? These are the coefficient functions, the ones multiplying y double prime, y prime, and y, unless those have very, very specific forms, to find a solution of the differential equation is generally going to involve infinite series, right? Power series, your favorite topic from Calc 2, okay? So, when can we find easier solutions? That's where we're gonna start. So we are instead going to, so first, we are going to start with section 2.2, okay, which is constant coefficient. That's an I. It looks like you need coefficient. Constant coefficient homogeneous. Start with another word, homogeneous. Second order ODEs. Whew, okay? We're making a lot more restrictions than this much more general equation, right? Okay, so constant coefficient by definition, by nature, right, is linear. Again, homogeneous we don't talk about unless it's linear. And second order, so how does this guy change, right? If we're going to write this more general non-constant coefficient, non-homogeneous equation, how do I write the ODE with constant coefficients? Well, it's good. Instead of it, some function of x, I'm going to use your lowercase letter, right? I would just have some constant a, right? Some number, constant a times y double prime, right? Not allowed to depend on x, right? Plus, you guys tell me? Good. B times y prime, yeah? Plus some constant c times y. Now, do I have to replace d with constant d? No, okay? This is not a coefficient, right? Constant coefficient means these three guys, yeah? That's the constant coefficient piece. What are we going to do with this piece if we're trying to satisfy these words? Yeah, gotcha, right? Very nice. Then if it's homogeneous, we can have anything here. We've got to be equal to 0, right? Okay, so instead of the crazy nonlinear looking thing that we started with, instead of this guy who's like considerably more general, right, than this, we're going to start with this. Constant coefficient, second order, homogeneous ODEs. Now, I want to caution you just a little bit. Section 2.2 in this book is remarkably short, and we're going to spend way more time talking about these guys, developing our understanding with these equations and the theory behind where it comes from. There's a lot more to what we're going to do than what's there, okay? All right, we will, come back and consider non-homogeneous ones of these guys later, much later. That's some of section 2.1 and section 2.5 as far as, if you're interested in where we're going. Okay, so, let's consider this ODE. I'm gonna keep referring to it, so I'm gonna call it star, okay? I'm just gonna introduce some other notation, right? This constant coefficient linear ODE, this is a linear combination of y prime, and y double prime, right? What's a linear combination? You multiply stuff by constants and you add them together, okay? Anyway, that word will come up later. So what does this equation say? It says, find me all functions out there in the world, y. Now, this is autonomous too, right? So, I mean, written this way, we could have the independent variable be x, the independent variable could be t, the independent variable could be any letter other than the ones that are up here, right? We'll take it to be x, just because, it's easier to write. You guys seem to like x. So, what does it say? What does this equation say? Find me all functions out there in the world, right? Where the constant a times the second derivative plus the constant b times the first derivative plus the constant c times themselves ends up being 0. Yeah, that's what it says, okay? Okay. Well, where do we even start? Okay? Well, let's think about something we know. We know something about first order equations. So let's pretend this guy isn't here. If we pretended that wasn't there, right? Then this would be a first order ODE, right? If the a was 0, right? If a was 0, it would be a first order ODE. It wouldn't be a second order ODE anymore, right? Okay? So if a was 0, what would you do, right? Then this is an equation. This is just our, you would take that guy and think about him moving across the other side, and that would just be y prime is equal to a constant times y, right? The constant would be minus c over b, yeah? Okay? Solving that guy for y prime. Well, what is the solution of y prime equals a constant times y? What function satisfies its derivative is a constant times itself. Oh, very nice, right? Good. E to the constant times x, right? Yeah? Okay? So if that works there, and all we're doing here is adding on another derivative of y and multiplying that by some constant, maybe, right? So here's our whole, thought process for maybe solutions of star might look like y equals e to some constant times x, if we're going to use x as our independent variable, right? So we could use k as the constant, but k is hard to write, and we could use all kinds of things. Sometimes lambda is used as a constant, but I'm thinking you guys might not like lambda. I'll just go with r, which is what your book uses for the constant. So r is this parameter, right? Where r is some constant. Okay? So we're going to guess, based on our experience and our knowledge of derivatives of exponential functions, our experience with first order problems, that solutions might look like this. Well, maybe you've seen some problems like this before, right? Okay, now you have an idea of why we tried to introduce this concept earlier. So what would happen if we assume that solutions might look like that for this guy's star? Well, let's plug in. I don't need this anymore either. So let's compute the derivatives for our guess function, it's a guess, right? Y equals e to the rx, yeah? So what would y prime be? Good, we're so good at this now, right? The derivative of e to the stuff is e to the stuff times the derivative of the stuff, right? I'm taking a derivative, this derivative means derivative with respect to x. So when I'm taking the derivative of the stuff, the derivative of r times x with respect to x is, good, r. R is like a constant, right? And then what is y double prime? Well, y prime is now a constant times this function. The derivative of a constant times a function is the constant times the derivative of the function. We just took the derivative of e to the rx, which is r e to the rx, right? And so therefore y double prime is r squared e to the rx, yes? Okay. So now what are we going to do? Well, we're going to plug into our differential equation. Plug into our guess into this ODE, this general, completely general, right, constant coefficient, homogeneous second order ODE. It doesn't get any more general than that for everything we just said, right? Okay? Plug in. Well, what do we get? So it's A times y double prime. What is y double prime? R squared e to the rx, right? Plus B times y prime. What is y prime? R e to the rx. Plus C times y. What is y? That was our guess. E to the rx, right? So we plug into the left-hand side of the equation, and then we're going to see what we get, right? So now let's just that's the left-hand side, so this is the left-hand side of STAR, okay? All right, so you look at that, and what is it screaming out at you to do? Yeah, good. Right, we got e to the rx in every term, so let's factor it out. E to the rx, right? And then what's left here? Good, AR squared plus BR plus C. Yes? That's about as much as we can do, manipulating the left-hand side, right? So what do we want to be true, right? We want this equals 0, right? Because that would be satisfying the differential equation, right? That would make this guy a solution of the differential equation, yeah? Alrighty, well, tell me about e to the rx. What do you know about, so I've got a product of two things here, right? What can you tell me about this piece of the product? Is that ever 0? Good, no, never. Is it ever negative? No, e to stuff is always positive, right? So that guy's always positive, and so if the product of this and this is going to be 0, then what has to be true, right? If we want that, then that says AR squared plus BR plus C must equal 0. Have you ever seen an equation that looks like this before? Yeah? Give me a name for this equation. It's a quadratic equation. Right? In R, right? Okay, it's a quadratic equation for R, so we're looking for roots, right? R of this equation, yeah? Okay, this equation is super awesome, right? It's a quadratic equation, it's an algebraic equation, yeah? So what did we just do, right? We just said, hold on here, if this is our ODE, this is our differential equation. We've seen that to solve differential equations, we need calculus. We need to be able to integrate, yeah? Okay? Calculus. But by making this assumption that we would have a solution e to the rx, we turn this differential equation into an algebraic equation. An algebra equation. So we kind of like change the dimension of the problem, right? We take it out of calculus and put it into algebra. That's kind of cool, right? And so this guy results in an equation that looks like AR squared plus BR plus C is equal to 0. In fact, that equation is so important, we give it a name and we call it the characteristic equation, because it is the equation that is characteristic of this equation. It's what's at the heart of it, okay, of this ODE. So if we can deal with this characteristic equation to solve for the R's, right, then we've got possible solutions for our differential equation. So we turn a calculus problem into an algebra problem. That's super cool, right? Okay, so let's see. Come over here now. So let's talk about that characteristic equation for a second. All right, so what do we know about this guy? Can we solve it? In general? Yeah, right? I hear you singing right now, right? How do we solve this guy? Quadratic formula, right? Okay, so right now we're doing this in generality because we're trying to understand something about these equations in general. If you're actually doing a particular problem, you would want to try factoring first, right? But we're gonna solve this by quadratic formula. So what does the quadratic formula say, right? I'm not gonna sing it. I didn't get that gift. All right, so what is R equal to? R is our variable, right? This is quadratic in R. R is equal to minus B plus or minus the square root of B squared minus 4AC all over good 2A, okay? Okay, so what does this tell us? Well, what this tells us is that we really have three cases to consider. Okay? What are those cases based off of? Think about this as a parabola, right? Okay? What are those cases based off of? In here. What's the important thing we need to pay attention to that's going to change the character of what's actually happening? Yeah, this guy. The discriminant, right? B squared minus 4AC, right? So case 1 is when B squared minus 4AC is positive, right? If this guy is positive, the square root exists, we get two different answers, right? Plus, because this guy's going to be just some real number, plus or minus that, you're going to end up with two real roots, right? Two real roots. So B squared minus 4AC positive, we get two distinct, different, right? Real roots for this parabola. So we'll call them R1 and R2. So R is equal to R1 and R2 would be the roots, and R1 is not equal to R2. Yeah? So what does that case visually? Visually, what does that mean, right? You know, so suppose I have, right, the R axis and I'm trying to graph this parabola. If I've got two real roots, then my parabola crosses the horizontal axis in two different places, right? So this parabola would have a B squared minus 4AC that's positive, right? Or if it, you know, it could open upside down, right? That's still fine, then A would be negative, right? But B squared minus 4AC is positive because it has two real roots, right? R1, R2, yeah? Okay, does that make sense? They're different and they're real numbers, yeah? On the R axis. Okay, that's one case. That's the only case we're gonna talk about really today, and we won't even finish talking about that, right? So there's quite a bit to go. What's the next case? Well, yeah, let's just kind of take it through its possibilities. What if b squared minus 4ac was identically equal to, it turned out to be equal to 0, right? Okay, this transitioning time. So then how many roots do you get out of here if this guy is 0? Square root of 0 is 0, so there's, you know, only one root that comes out. Does that mean we're missing one? What's the deal with the parabola in that case? We get one repeated root, right? One repeated root, just in R1, period. Yeah? What does that look like, right? That would look like a parabola that just touches the axis, right? And then goes back up, right? Or maybe does this, yeah. Yeah. One repeated root, yeah? Okay. So you only get one root out of there. Talk about that later. Let's just mention what case 3 would be. So what would case 3 be for our possible roots that come out of here? Very nice. b squared minus 4ac is negative, right? If that's the case, I'm taking the square root of a negative, and so what happens back in algebra class? What is that? Good. Complex conjugate roots, right? Yeah? 5 plus or minus 3i, right? 5 plus 3i, 5 minus 3i, right? Just as an example, complex conjugate roots, right? Okay, so what does that mean about your parabola? It never intersects the real axis, right? It never intersects the r axis, right? The roots of this function are complex conjugates because they don't have, there are no real roots. You never intersect the horizontal, right? Or something like that, right? Okay, make sense visually? Okay, so we're in this case, we're gonna reduce solving the constant coefficient, second order, homogeneous ODEs to understanding what's happening in these 3 cases and how that then feeds into our solutions of the differential equation, okay? All right, so let's think about case 1. Okay, I'm gonna erase these guys now, yeah? Okay, so in case 1, what do we have then? We came up with 2 different values of r for which we have solutions. So we actually have 2 solutions, right? So this would, case 1, oops. Case 1 implies there would be some solution, let's call it y1, which would be e to the r1x, right? One of those roots, right? And some other solution y2, which would be e to the r2x, right? Now, to find those guys, you wouldn't have done quadratic formula, we just would have tried to factor this guy. Okay, maybe we should do an example. Do I want to do that right now? Not quite yet, okay? All right, so here, right, these guys are real, so we'll just say, make sure we are clear about that, R1 and R2 live in R, right? Does that make sense? Okay. I'm gonna erase our characteristic equation. Notice, right, when I have a second order constant coefficient ODE, what is that? How does that translate to a corresponding algebra equation that is characteristic underlying this guy, right? Second derivative, second power. First derivative, first power. Zeroth derivative, 0 power, right? Something to 0 is 1, right? There's really a 1 times this, right? Okay? So you don't have to do what we did each time. you know that you look at a second order constant coefficient differential equation, and then you write down the characteristic equation that goes with it, and then you try to factor that and solve it to find the R's, right? Okay, so well, what did we just say? So this, we got these two solutions, right? Came out of case one, okay? So y1 equals e to the r1x is a solution of star, this guy, and y2 equals e to the r2x is a solution of star, yeah? But, you know, like, what if, so what does it mean for that to be a solution? For that to be a solution, it means that a times y1 double prime plus b times y1 prime plus c times y1 is equal to 0, right? And what does it mean that for y2 to be a solution? That means a times y2 double prime plus b times y2 prime plus c times y2 is equal to 0, right? That's what that means. Well, let's just for fun say, well, what if I add these two equations together? What if I add the equations? Okay, suppose I add them. So I'm gonna like do that, yeah, that's legit. So if I do that, right, I'm gonna get a y1 double prime, plus, I'm just gonna do it this way, plus a y2 double prime, right, plus b y1 prime, plus b y2 prime, plus c y1 plus c y2, right, adding the left-hand sides, is equal to 0 plus 0, which is 0. Very nice. Okay. So, well, as I look at this kind of thing, you know, I could have written all this first and then written all of this and then rearranged, just trying to save myself a little bit of space. And so this guy, I'm like, hey, wait, these two terms have a c in it, so I'm just going to factor that c out, and that's c times y1 plus y2, right? And we're going to bring e equals 0 down there. Just rewriting this algebraically. Well, these two terms have a b in them, right? So that's the same as plus, if I factor that, those two terms, y1 prime, factor the b out, right? Then I have y1 prime plus y2 prime there, yeah? And this guy, these two terms have an a in them, so y1 double prime plus y2 double prime. All I did was factor out in each of those little pairs, right? Okay, but I'm going to keep working backwards this way just for fun. I've got y1 plus y2 there. Okay, well, what do we know about, like, so if I think about this term right here, this little piece, y1 prime plus y2 prime, that's the sum of the derivatives of two functions. But what do we know from calculus? The sum rule says well, we usually say it, the derivative of a sum is the sum of the derivatives, right? So the sum of the derivatives is the derivative of the sum. Yeah, right? That's another way to write that, that's correct. And then because of that, we have the same thing with the double primes, right? The derivative, the second derivative of the sum is the second derivative. The sum of second derivatives is the second derivative of the sums, right? We're allowed to do that with properties of differentiation. Well, what does this equation mean? Oh, it's kind of nice that it's written right here on this same level as star. I didn't even plan for that, right? What does that equation there mean? A times the second derivative of some function plus b times the first derivative of that same function plus c times that function is 0. And what is that function? The function is y1 plus y2, right? So what does that mean, right? The function y1 plus y2, if we take those two guys and we add them together, right, that also satisfies the differential equation. y1 plus y2 satisfies the ODE star, right? Okay, well, so what does that say? We had two solutions, we can add them together, and there's still a solution of the differential equation, okay? Well, that, we're kind of striving toward, well, what's the most general solution? We aren't going to justify that today, but we'll just see what happens here. So we can add solutions together. What if so last time we added those equations, what if oh, that's this, okay. Did I ruin this red? Maybe. What if I multiply, here's this equation. Yep, I'm not gonna be able to use that red. Sorry there. What if I multiplied, so y1 is a solution, therefore this is true. I'm purposely doing this in more generality because it doesn't really matter that it's these two guys, right? It just matters that we had a solution, okay? I think I just answered somebody's question out there. So what if we multiply this by some constant, okay? Let's just say, C1, okay? What if I multiplied that by a constant, say C1, this equation? So I know that since y1 is a solution, this equation has to hold. So if I multiply this whole equation by some constant C1, when I do to one side, I have to do to the other side, right? Good, okay. Okay, well, this side over here is still 0, and this side I can now distribute through that C. So what do I get? C1a y1 double prime plus C1b y1 prime plus C1c y1 is equal to 0, right? But I could also write that as a times C1 times y double prime plus b times C1 times y prime plus c times C1 times y is equal to 0, right? Can you see the green? Maybe this green is better. So in the same way that I was striving for something here, we're similarly striving for something here. C1 is just some constant. Any constant, okay? Let's work backwards this way. So I already kind of wrote this C1 times y, yeah? Here, I've got my constant b, and then I've got C1 times y1 prime. So this is a constant times the derivative of a function. The constant multiple rule in calculus says that is the same as the derivative of the constant times the function. Yeah? Whoops, y1, I missed that one there. Thanks, somebody out there was yelling, you missed the one. Okay. Same thing here, right? I can write my a times the exact same reasoning we just had there. If I take the second derivative of C1 times y1, I'm going to get C1 times the second derivative of y1 because of our constant multiple rule for differentiation, yeah? So similarly, what does this guy say? Well, it says if I have a solution, y1, and I multiply that solution by a constant, any constant, just called it C1 for no reason, then any constant times a solution is also a solution to the differential equation star, right? Because this satisfies A times second derivative of thing plus B times first derivative of that exact thing plus C times that thing is 0. And that's what this equation says has to be true, right? So C1, Y1 is also a solution of star, yeah? Okay, well then, we know we can add two solutions. If we have two solutions, we know we can add them and we still have a solution. If we have a solution, we know we can multiply it by a constant and still have a solution. Well, so then we could multiply this whole thing by a constant, or each one individually by different constants, right? Because C1 times Y1 is a solution, and C2 times Y2 would be a solution, and then we can add those two guys together and get a solution. So, we will hope in a little bit we'll justify later that all solutions, right? All solutions can be represented by all solutions to star can be represented by function y of x is just, if we have two explicit solutions, we can multiply one of them by a constant and then multiplying the other one by a constant. This is due to the linearity of what's going on here. We'll explore that in a little more. So, in case 1, what would that say then? That would mean that solutions have the form that all solutions, haven't justified that yet, we will later, all solutions have the form y of x is C1 times Y1. Y1 is e to the R1x plus C2 times Y2, right? Y2 is e to the R2x. Yeah? Okay? We gotta stay tuned for we will justify later. Yeah? So let's do a particular example. This idea of an argument you kind of already saw earlier when we were doing first order existence and uniqueness. And this process we're going to simplify a little bit because it's a lot of writing by introducing some operators later. So, this is a written out version of it. So don't get afraid of what, we'll see a little bit later. Okay? All right. But more generality that might be appropriate for more general coefficients as we move along. Okay, so let's do an example, okay? You can look at, there's an example at the very beginning of section 2.2, and I'm going to do a homework problem very similar to one of your problems. Now, with specific numbers, right? You're excited. When are the specific numbers coming? Too many letters, right? I heard it, but no, definitely not too many letters. Okay, so this is our claim. We're gonna go with it for now. We still need to justify, right, that there aren't others out there, right? We just justified that this is a solution of that differential equation, okay? In the case when we have two distinct real roots, but we haven't justified that there aren't others. Some crazy wacky function out there that doesn't, look like this, that's also a solution, okay? It'll be nice. I know you'll feel better and sleep better when you realize, well, there aren't any more. This is everything, okay? Let's look at a particular example, okay? So, again, like I said, read the example at the beginning of section 2.2. Here's another one. This is exercise 2.2.9, okay? So we're gonna solve, and as I said, it's gonna take a while for us to get through section 2.2. It looks like dramatically short in the book, but it's actually significantly longer. All right, so solve what? Here's the equation. Y double prime plus 9y prime is equal to 0. And then we're gonna throw on some ODE, some initial conditions as well. Y at 0 is equal to 1, and y prime at 0 is equal to 1, okay? All right, this is our ODE. Our second order problem, it's a second order constant coefficient. 1 and 9 are the coefficients. It's homogeneous because we're set equal to 0. Everything involving y is on that side, or where its derivatives is on that side of the equation. And these guys are my initial conditions. We've already kind of talked about the fact that a second order problem is going to need 2 initial conditions, right? And we kind of see it in our, our claim that this is the general solution in this case. So, because we have these 2 arbitrary constants, kind of 2 degrees of freedom. And so in order to determine the unique solution, you would need 2 extra conditions on the solution so that you could solve 2 equations for 2 unknowns, yeah? Okay. 1 equation for 2 unknowns is going to give you still infinitely many solutions, right? Okay, so this is our IVP, right? This is our IVP, and let's see what this is asking us, right? Find me all functions out there in the world whose second derivative plus 9 times this first derivative is 0. There's infinitely many such functions. Maybe you can kind of see one right now. And then what is the initial condition saying? Well, visually what it's saying, here's x and here's y, right? Y of 0 is 1. Well, that means when x is 0, y is 1. That means this point, the point 0, 1, is on the graph of the solution to this differential equation as well, right? There's infinitely many solutions out here, but this point is on the graph. But that's not enough to pick out a unique one like we did with first order. So what else do we get? What is this telling us about at 0? Yeah, say it loud, say it loud. Here we go, right? This is telling us about the slope of the tangent line to the solution at 0. So what does that say? The slope of the tangent line to the graph of this solution when x is 0 is 1. So what do I know, right? The tangent line here, my little slope line, it's not a slope field, it's just a single value of a slope, right? That slope is 1. So that when a solution crosses here, it's got to cross with some slope of 1. It might do that. It might do that. Pretend that the slope of 1 is like, right? But we have some understanding of how the solution has to cross there. It doesn't cross steeply like this, or like that, or more steeply like that, right? It crosses with a slope of 1. Yeah? Okay. So now let's just dive into this process. Here's our ODE. There's a variety of different ways to solve this equation because our y is missing. C is 0. We're not going to plug into there, right? What do? Right? We write the characteristic equation. what is the characteristic equation that goes with this ODE? Good. Y double prime turns into an R squared, right? We understand why. 1 times R squared, because it was 1 times Y double prime. Plus, good, 9 times R, right? Y prime turns into an R to the 1, right? Take our differential calculus thing, turn it into algebraic thing. And then we don't have anything else out here. There is no plus 5y or something like that, right? So otherwise you would have a plus something there, but it's not there, right? So you've got 0. All right, how do we solve this equation? We don't use the quadratic formula, right? What do? Factor, very nice. So we factor out an R, we got R plus 9 is equal to 0, yeah? So what does that tell us? I've got a product of two things equal to 0. The only way that's gonna happen is if one of them is 0. So either R is 0 or R is -9. So we found our two values, right? Okay, so we'll say R1 is 0 and R2 is -9. We are in case 1, not because we checked b squared minus 4ac is c, is positive. That's not what we did. How do we know we're in case 1? We wrote down the characteristic equation and we got two distinct real roots, right? 0 and -9 are both different real numbers. Yeah, they're both real numbers and they're not the same real number. Yes? Okay? Awesome. Okay, so that produced for us the ability to then say what our solutions are, right? So remember, right, how did we get from here to here? Y is e to the r, x is behind the scenes, right? This is behind the scenes. Yeah, that's how we got there. And so what is this guy giving me? This is giving me a y1, which is e to the r1x, right? What is r1? 0, right? E to the 0x, right? And that's what my r1 is. What's my y2? It's always good to say what y1 and y2 are. Don't just jump straight to here, okay? Y2 is, my r is -9, right? So e to the -9x. Yes? You're right. This guy simplifies, right? Good. Okay, so what is y1? What is e to the 0? Very nice. So y1 is really just 1. Maybe you saw that to begin with, right? Okay. Now, right? Any constant satisfies this differential equation. Yeah? Okay, any constant. Because if I take the derivative of a constant, what do I get? 0, right? Second derivative is still 0. 0 equals 0. Done. Yes? Okay? But this guy is kind of a special particular constant, or special constant. And so we have our two solutions. Y1 is 1 and Y2 is e to the -9x. Yeah? Okay? Now, before we like go and jump and claim this is our general solution, did anybody see another solution of that equation that cannot be written? Well, let's see, how do I want to say this? Yeah, let's just say this. So maybe you would have guessed y1, that 1 was a solution. But I don't think you would have, right? What is the constant that you would have guessed is a solution based on what we did in some of the first order stuff? Okay, so let's note over here, note. What also is a solution of that? Y equals 0 is also a solution, right? Y equals 0 solves this guy, yeah? Okay? So, what we did when we were on that board, saying if we have two solutions, right, then multiply by constants, add them together, get a general solution. Well, that's not completely true. Because suppose we would have just been like guessing, right? Maybe we were just guessing. We wouldn't have gone through this process. We would have kind of ignored this. And then you would have been like, hey, wait, y equals 0 is a solution. So I got one solution. We'll call that y1. And then I magically guess e to the -9x is a solution and check it get a second solution. So I have two solutions, and I'm going to call them y1 is 0 and y2 is e to the negative 9x. And then I'm going to claim that c1 times y1 plus c2 times y2 is a general solution, and I'm going to be wrong, okay? And so there's actually a little bit more to the story. It's not find any two solutions, multiply them by constants and add them together, and you get a general solution, okay? We'll get to that chapter of the story in one of the next videos, okay? So this guy is also a solution, but he's not one that we could call y1 and then expect to say c1 y1 plus c2 y2 is a general solution. So that's something to pay attention to. So what does this piece tell us then? And this idea right here then say we want to call our general solution, which we'll justify later. This would say that our general solution for this problem would be y of x is equal to c1 times y1. What is y1? 1, right? Plus c2 times y2, which is e to the minus 9x, right? If I do that, then notice, is the solution y equals 0 contained in this solution? Yes? No? Yeah. If I make c1 and c2 both 0, right? Like if c1 and c2 are arbitrary constants, right? They can be any real number. So if I make them both 0, then I get the solution y equals 0, right? So this solution is contained within this. But if I had picked 0 instead of 1 and put a 0 here, then I would not have been able to get all of the solutions. Does that make sense? Okay? So it's more than just finding any two solutions, multiplying them by constants, add them together, and claim you have the general solution. So what's the extra thing? That's what's coming next video. All right, so here's our general solution for this guy, and now we still need to find the constants to satisfy the initial value problem. Okay. So there's infinitely many functions in the plane, but they all have to look like some constant plus some other, so c1 plus c2 e to the negative 9x, right? These are our possible solutions. So all the infinitely many solutions in the plane have to look like this. So now what about the initial conditions? Okay, let's apply those. So we've got, I'll just write y of x again, c1 plus c2 e to the negative 9x. I'm going to need y prime of x. I'm going to compute y prime from here, right? So what is y prime? Derivative constant is 0. Derivative, I get my constant c2. Derivative of e to the negative 9x, e to the negative 9x times negative 9, right? Okay. So now I have those two guys. Now I'm going to evaluate y at 0. What is y evaluated at 0? c1 plus c2 e to the 0, right? Well, that's just c1 plus c2. Yeah? What do I want y evaluated at 0 to be? I want y at 0 to equal 1. So here is my one equation for two unknowns, right? What about y prime? I have my y prime of x. You gotta have the general thing first before you can evaluate. What do I want to do? I want to evaluate y prime at 0. So if I plug 0 into this equation, what do I get? Negative 9c2 e to the 0, right? Which we know is 1. So negative 9c2 is what y prime of 0 is. What do I want y prime of 0 to be? I want it to be 1. Yeah? And therefore, this is my second equation for my two unknowns. All right, so this is a nice, simple, easy one to solve, right? How do we solve these two equations and two unknowns? C2 is -1/9, right? And then what is the next equation? Would C1 is 1 minus C2, which is 1 minus a -1/9. Right? Yes. Which is 10/9. Yeah? Be careful with your negative signs. It's always super easy to drop a negative here, so I am like double checking a second. 1 minus C2, yes, 10/9. Okay, so C2 is -1/9 and C1 is 10/9. Right? 10/9 minus 1/9 is 1, yay. And so what would then be the solution of our initial value problem? I'm giving you time to write it down. So this is something we also need to justify. This initial value problem would have a unique solution. Okay, so gotta justify this. The unique solution of this initial value problem is what? Well, y as a function of x is, what does C1 have to be? 10/9. Right, I'm looking over here now, right? C1 plus C2 e to the -9x. So C1 is 10/9, C2 is -1/9. Minus 1/9 e to the -9x. And that picked out those two explicit constants that gives me a unique solution, the only function whose derivatives satisfy this, that goes through this point with this slope of a tangent line, is that one function. And that's kind of awesome and cool, right? Okay, so now you can see why we're gonna wanna justify all of that stuff, because, you know, that's pretty amazing. Let's see. Okay. Again though, right now it's just a claim, right? We don't know, maybe there is some other wacky function out there because we don't have a theorem yet that tells us this is legit, yeah? We're just making stuff up, okay? Making stuff up that looks good. So let's write down the theorem before we go here, okay? Maybe I'll leave that there. I'm just gonna erase this, I think. Oh, the other thing I wanted to mention, right? When we had talked about like 0 being a solution, if we had used that as our y1, right? Then we would not have been able to find unique coefficients, constants C1 and C2, so to satisfy those initial conditions. So we would not have gotten a solution of our differential equation, of our initial value problem. So again, which two solutions you use seem to be important. And why is it only 2? Okay, anyway, let's write down a theorem. We're not going to prove this theorem right now. We're just going to write it down and marvel at the result. Existence and uniqueness for second order constant coefficient homogeneous, right? IVPs. That's what this theorem is. Okay? All right. So what does the theorem say? How do I say that? There exists a unique, right? There exists a unique solution to the initial value problem. Okay, here it is. A, y y double prime plus by prime plus cy equals 0. You knew it was going to be that, right? Because why? It's second order, constant coefficient, homogeneous, right? That's it right there. That's the words, that's the math, yeah? Might just need a little bit more space. So for the ODE, A, B, and C are real numbers, okay? And A is not 0. Why should A not be 0? Good, it's not second order anymore if A is 0, right? So A, B, and C are real numbers, A can't be 0. Either of the other guys could be, it doesn't matter. Okay, and then the initial conditions. And there's lots of different books use different notation for the initial conditions. Y at X, since we're using X, we'll use X naught. If you use T, you usually use T naught. So Y evaluated at X naught. And normally in first order we said it's equal to Y naught, but we're not going to use Y naught. We'll see if you can figure out why. So I'm just going to use alpha. Okay, it's alpha, just a little Greek letter alpha. So the initial condition for Y at X naught is alpha, and Y prime at X naught is beta. Very nice. Okay, good. Alpha and beta are real numbers. Okay. Y, usually when people use a Y naught for this, they use a Y1 for this, but we're using Y1 for one of the solutions of the differential equation. The other option is the Y naught and Y naught prime, but that always makes students nervous. Maybe Greek letters make you nervous too. It's okay, you'll survive. Right. Okay, wait, boom, there it is, right? Actually, there's more. This is now guaranteeing us, with some justification to why this theorem is true, that if we have a constant coefficient homogeneous ODE initial value problem, we have a unique solution, period, to the initial value problem. And furthermore, remember how like there could be crazy things where you're gonna blow up in finite time, right? Okay, when you think about the limit as x would go to infinity, or even at some other crazy point that something might just blow up, not unexpectedly. You can't tell from the differential equation, and how we saw that in first order. Furthermore, the solution is valid for all x real numbers, right? So x minus infinity. We don't have that, okay? Finite time blow up thing, okay? So that's pretty cool, right? So when we're solving these guys, we know we're in great shape. That's just nutty, right? That's just nutty, okay? Super nutty. Maybe not terribly like unexpected, because if I've got constant coefficients, remember the coefficients were like a problem in first order, and constants are continuous everywhere, and therefore there's no continuity problems coming from the actual ODE itself, right? What else do we want to talk about? So let's see, we're closing things up here. This means that it's always possible to find the constants C1 and C2, okay? So as long as you pick your Y1 and Y2 properly, you're gonna always be able to find a unique solution to the two equations, the two unknowns that come out of the initial condition, okay? Last thing to mention. So think about this, right? We talked about if A was 0, but if B and C were 0, right? Then we would just have Y double prime is equal to 0, right? If B against 0, 0. This is the simplest possible second order, right? Simplest possible second order ODE, right? Constant coefficient, everything else is 0, coefficient of y double prime is 1. Okay, well, so what are all the types of functions that have a second derivative always 0? Good, lines, right? Y has to be a line, y is all lines, right? Yeah, makes sense? Infinitely many solutions, right? C1x plus C2, yeah? Okay? All possible lines, yeah? Or in fact, actually, we might want to even write it more like C1 plus C2x, but anyway, not that it matters. So there's many, many lines in the plane, right? How do we pick out one unique line? We specify a point, right? Y at x naught equal alpha is saying the point x naught alpha is on the line, right? So we specify a point, here's x, here's y, here's x naught, here's alpha, here's the point x naught alpha, it's on the line, right? For generic alpha. Y prime at x naught equals beta is giving you the slope of that line, right? The derivative is the slope. So once I know the slope, I have a line, yeah? So for a line, all I need is a point and a slope, and I can write the line equivalently, right? A line is really this second order differential equation, yeah? So what this theorem is saying is kind of cool if you think about it as like, okay, let's talk about this much more general second order differential equation, the most general second order differential equation with constant coefficients, okay, that's homogeneous. So it's a generalization of that guy. And we're still saying, in order to be able to pick out the one function that satisfies this requirement on how its derivatives interact, all we need to do is be able to say one point that's on the solution and the slope of the tangent line as the solution passes through that point, and we can uniquely determine the one function that would satisfy that specific equation. Now that's super cool, right? That's just super cool. With a point and a slope, we can determine even in this more general case, yeah? So that's kind of awesome. All right, well, think about all this fun stuff. There's some problems that you can work on. There's not a lot you're going to be able to do until we talk about the rest of the other cases and we justify a little bit more of the theory, okay? So it's been fun embarking on our new Chapter 2 adventure with you.